Well, yeah, so just to go over, the first presentation is going to be on basically Duke Energy's damage monitoring system, and I'll be doing this presentation with Eugene Eagle. So, Eugene, I'm going to let you start. I'll advance kind of next slide.
And you said you wanted me to go ahead and get started with the presentation?
Yeah, can you see it now?
Yes, yeah, I can see it. Okay, hey, good morning or good afternoon to everyone, wherever you're located. My name's Eugene Eagle. I'm a HRSG engineer for Duke Energy, based in Raleigh, North Carolina. So today's presentation is we're going to talk about the damage monitoring system that we installed at one of our combined cycle facilities in eastern part of North Carolina. And I'm gonna start off here and go over some of the goals for the monitoring system, the summary of what it took to implement the um, the program and which components we decided to choose to monitor, and some of the goals of the program and why we implemented it, and then some of the future plans for monitoring. And then Kane will get into more depth about the actual monitoring system, how it comes up with the results that it does, and what we're starting to see with the damage monitoring system. So next slide. So what is an online monitoring system? So we take existing instrumentation that's already installed on the unit, things like temperature, pressure, steam flows, valve positions, and then we added additional temperature instrumentations. There was over 64 instruments per unit, so we could get the exact temperatures of various components. And all this instrument feeds in to the structural integrity software. It's called Plant Track, and it goes through our Pi server, through a Pi historian, and a VPN connection. So it's very secure. It's a one-way route with through firewalls and things like that. So we send the data over to structural integrity, and they have their Plant Track software that they use to collect the data, to analyze the data, and then it gives us some good results for things like creep life and fatigue life, and it looks for high temperature differentials, and can give us alerts when something is abnormal or there's a component that's accruing more than normal damage. So that's kind of a overview of what we're looking for and what we're trying to accomplish. Next slide. So I got into this a little bit already. So it's a real-time damage tracking system for our HRSG and also several HEP components, and we're using SI's software and their system. And the Pi is the interface to collect the data. So our first site, or pilot site, we installed this system in 2021 initially, so it's been running ever since then and collecting data. We chose a combined cycle plant in eastern North Carolina. It's a 3-on-1. The plant went commercial in 2012. So of course, as part of this, we had to collect all that historical operational data to give to SI so they could go all the way back to commercial operation to start analyzing these components. This site is currently in base load and load following operations, so not a lot of cycling yet, but we do anticipate in the future that because of renewable load growth and changes in our loads, that the combined cycles are going to they're going to have to start cycling more often. So that's really where this program will show a lot of value, because of all the wear and tear that the components will take as we start to cycle these units more. Kind of already got into the instrumentation, how we're using the existing instrumentation, and then we installed new thermocouples on things like tubes and headers and attemperators, places like that where we could get very specific temperatures and differential temperatures. So the units are Vogt OEM with a Siemens combustion turbine, triple pressure duct fire. They do have the bypass stacks. So at the time of the project, when we installed the additional instrumentation, it was around 70,000 hours per unit. And we have had a lot of issues historically on these 3 units. We've already replaced all the HP interstage attemperators due to cracking in the internal liners. A lot of that was related to conditions during early operation, like a temperator overspray. We also have had issues with block valve leak by. A lot of those things have contributed to damage in our attemperators, and also visible indications of some thermal stress, such as some bowed tubes in a reheater section, for example, that was related to a temperator overspray and a temperator operation. A lot of those things we have been able to address. We've upgraded the temperator control logic to help avoid some of these overspray events, and also the drain logic has been tuned to perform better during unit startups to remove condensation from the system. So a lot of work's already been done to improve the units, and so this is really going to add an extra level of monitoring to look for issues and problems that we can continue to address and improve upon. So next slide, Kane. So what components are we monitoring? You know, I'd already mentioned we're looking for creep damage and fatigue damage. We're calculating, you know, what's the creep life of a component? When do we expect it to get towards the end of life? You know, when we may need to replace a component, for example, or start to plan projects to replace those components. We're also looking at fatigue life. Anywhere you have you expect to have a large temperature differential that could cause stress and cracking, you know, we want to monitor that component. And you also have that, I guess, capability to look at your creep fatigue interaction and corrosion fatigue, and then oxidation and exfoliation as well. Those are some other goals of the monitoring. So what components we're going to monitor? This is anywhere that has a high temperature and a thick component, you know, that could lead to some creep damage if it's high temperature. So our hottest areas like HP superheater outlets, for example, you know, HP superheater tube to header weld connections. Anywhere we might expect some fatigue damage. The HP drum's a great example. It's a thicker component that has a welded connection to your downcomer. That's a high risk area across the industry where people have found cracking. So that's something we can help to monitor for, and that'll help us to determine when we may need to go in and inspect and start looking for cracks to develop. Anywhere there's an attemperator is a high risk area. I mean, you're obviously spraying relatively cool water into a very hot component. If something goes wrong or something breaks, like a nozzle breaks off, for example, then you could create damage very quickly. So anywhere there's an attemperator, we have monitoring capabilities around those areas. Also branch connections such as T's, Y's, Olets, and then I'd already mentioned some of the final stage outlet headers like your HP superheater outlet and your reheater outlet. Next slide. So our goals for monitoring, why did we want to do this? Because obviously this was a very expensive project. We had to install the additional instruments. We had to get it to the DCS. That required a lot of wiring in the field, as well as the DC input and output cards. So it was pretty big expense, but the justification for it and the benefits really outweighed that. We had a really good ROI on this project when we analyzed it. So one thing I'm excited about is just finding problems quickly. If, as I mentioned earlier, if something broke, like an attemperator nozzle, or if you had a poor control logic, for example, and you were getting some weird differentials downstream of your attemperators, you can pick up on it very quickly, and you can go in and address that issue as soon as possible or during your next planned outage. Same thing, there could be a spray valve leaking by, putting water into your system, or you could have a pressure, bypass pressure control valve that's leaking by and causing high temperatures downstream. You're going to be able to pick up on those indications immediately and then take action to correct it before it causes any significant damage. Also, when you plan for your HEP inspections, this should help you target which components to inspect, which components are going to be the high priority areas because you're seeing, accelerated damage. Should help you reduce your HEP inspection budget and just go after the areas you expect to have findings or potential for findings. Project planning, as I mentioned earlier, if you see a superheater header that's showing it's coming towards the end of creep life, you can go in and do validation of the data and then go ahead and put projects in to replace it if it's getting close. So better efficiency with projects and understanding when components are going to fail before they, you find them before they find you. Managing our components. These are big units for us, important units. They're highly efficient, and if we can get the maximum life out of them, if for example, if it has a 30-year design life and we can ramp those units a little bit harder or cycle them more and still get the 30 years of life out of the units, this can help us determine how aggressively we could ramp the units, for example. So maximizing the asset, getting the most value out of it, that was a big benefit. So just going to check, see if I covered everything. We're able to compare the 3 units to each other, and that kind of helps us to determine if there's any standouts, because all the units are identical. They should be operating in a similar configuration, similar loads, similar temperatures. So if something stands out, we can kind of key in on that and figure out, is that an instrument issue or is there something going on with this unit that we need to investigate in a little more detail. And it talks about process changes, control logic, for example. Maybe a drain didn't open when it was supposed to, and you may see a large differential between a couple of different superheater tubes. That would help us key in on that, and we could go in and take corrective actions. So I think I've covered most of the goals for monitoring and the benefits, Kane, and I believe this next slide is yours, isn't it?
Yeah, you've kind of already touched on this. Eugene was just showing the instrumentation. I mean, basically the general idea, right, was that most plants are set up to monitor basically process variables, and it's not so much geared at specific component life management. So, that, as you said, that was one of the areas then downstream of the attemperators, for example, where we had to install additional metal thermocouples to kind of, look for potential, large temperature differentials, fast rates of change, stuff that's going to drive fatigue damage. So this is an example from one of the interstage attemperators. I think the last one then was just, as Eugene said, we did one plant as a pilot site, but they've enjoyed and seen some benefit from the monitoring, such that we're already implementing this on 2 additional plants, continuing to enhance the product that we have, and then there's plans to continue adding additional sites so that they can do comparisons going forward. So with that kind of background, I guess I just wanted to quickly define high level what it is we're doing for the damage monitoring and kind of what the levels are, and then go through a couple of the case studies of what we've seen so far from monitoring Duke's one site, and I'll talk a little bit about the damage results and kind of additional challenges we encountered along the way of implementing the system. So I won't read through this slide. I mean, basically the 3 levels of monitoring kind of boils down to detection, then like actually doing trending, and then analysis and diagnosis to prevent. So from the very basic standpoint, detection is having those local temperature measurements, and certainly there's other instrumentation, but having that data available to you to tell when there are significant damaging events is number one, the great for a life management program for for your HRSGs and HEP, just because it gives you at least that knowledge on how to go about, deciding, do I need to change control logic here? Do I need to prioritize inspections? I mean, just having that is great. The next level up, aside from just detecting when you're having events, is, developing a trend and seeing, are things worsening over time? So in one of the later presentations, Wes will get into, there's some uh, uh, systems that we've been monitoring that they look good on first pass, but if you look at their historic trend, there'll be an increase in temperature differentials versus time, and if you dig into it, it's often because valves are slowly leaking by more and more, or the amount of spray has been increasing on attemperators, or there's leak by around baffles, and tubes are heating up higher on the sides of HRSG. So just basically the next level is adding in that historic basis and trying to trend different operating events over time so that you can better make decisions. And then the last level that really we've been getting into with Duke specifically is, okay, now I know that events happened, and certainly I know that I need to address them, but how do I assess the urgency if I may have had, 10 100-degree temperature differential events on one attemperator, and I've had one 400-degree differential on another attemperator? Certainly, I'd love to look at both of them and assess what's happening, but you need some way to prioritize basically what the urgency, which one is more damaging to that component overall. So that's kind of the next step, is using the additional instrumentation that was installed to ultimately build into a damage model. And certainly there's always going to be complications with damage models, because with any analysis there's assumptions, but we're basically trying to build the best analysis we can with the information available. So I would say generally when you're doing monitoring, you're going to try and be conservative on a lot of these damage calculations up front, just because you want to be on the conservative side of things rather than have a failure. So as Eugene said, I'm going to jump through a couple of these operating slides, but you can kind of see, the plant that was installed. This is the 3-unit loads versus time. And the blocked out areas is really the only times they've shut down. This is earlier this year for the 1 unit. So there's a lot of load cycling, but not a lot of shutdowns. And if you get into it, one of the aspects of monitoring and trending is, you want to be able to identify which conditions are driving the most damage. So this is a plot of load versus time, again, just overlaying the 3 units, showing that Duke generally operates them simultaneously. So we shouldn't be expecting very different trends when we get into the data. I guess I'm going to get through a little bit of this, but this is plotting that load versus time on histograms instead. So you can see when we're looking at how Duke operates the unit, one of the things we're looking at is what operating bins, low loads, intermediate loads, high loads, with or without duct burners, are going to be the most damaging versus time. And you might think for creep, it's generally going to be the highest temperatures, hottest pressures, but that's generally not the case when you're dealing with, attemperators and bypasses and, intermediate conditions between those. So this is, I guess, just one slide that was kind of showing that load versus time and how we can categorize it. But once you can identify the operating periods, you can identify the transients between them. So for each of the kind of components that we're monitoring for Duke's fleet, we're also building this historical trend of hot, warm, cold cycles on the units versus time. So this would be looking over all time. It's not just the plots of this year, but you can basically build these transient cycles for areas that you want to monitor. So in this case, the top plot is showing a hot, warm start, then the middle is a cold start, and the bottom is a hot start, showing that there's the most variations in hot starts. But generally what we're trying to build from this in forecasting going forward is, what is a historical trend in these transients? What is typical average rates to use for forecasting damage going forward, as well as, forecasting going backwards before the instrumentation was installed. So there's always a little bit of a caveat there of, you don't know exactly the operation prior to the installation of additional, local thermocouples, but generally, you're going to have to make assumptions and see where you land, and that's where ultimately all monitoring that we're doing is kind of, us accompanied by inspections to baseline and validate, the accuracy of the model. So if our damage model says you should have reached 100% damage at one point and you did an inspection and you didn't find damage, then that's good news. It gives us some knowledge to back off on the conservatism or to back off on some of the historic forecasting. So this is generally, and I'll just go through the dashboard. It's basically what we do is calculate damage for each of the components that Eugene mentioned, and or categorize events on those, and then we subtract off, either hours, or we track damage percentages. So it depends on the component, but basically, we build up for each component an immediate health status, which is, the TCs are on all this and all the other instrumentation is functioning. That might give you one immediate check on whether or not we need to switch instrumentation. There's going to be more of a short-term check on, basically how much life has this consumed in the past 90 days, for example. And then there's going to be a long-term check on how much damage has this consumed over the life of the component. And ultimately, we're tying all this information in to, work with Duke on their future inspection plan. So if they had done an inspection and we see that, hey, there's not accumulating much damage, then that gives us justification to push that next inspection interval out. Or if there's one that is having an attemperator problem or another fatigue problem, for example, we might accelerate and push it up and say, hey, it'd really be good if you get some more instrumentation even, or better dimensions, or get some material chemistry on the section. So it's all kind of linked together, but monitoring is kind of the overarching, I guess, driver to how we're tying it all together. So with regard to this, I just wanted to show one header kind of, and Eugene mentioned it. In general, we're monitoring multiple locations on each of the high temperature headers. So, you're looking at creep damage on end caps, on borehole ligaments, on tube to header connections, and on the outlet saddle welds. So there's a lot we can get into in this specific damage calculations that will extend beyond our time here today. But I kind of wanted to give an overview of what we're doing for headers, for example, and show one example. I mean, this is just a plot of creep damage versus time, but one of the examples on the headers that I wanted to show is for the HP Superheat 1 inlet, which is shown up here in the top left. And you can see Duke had already added a number of tube-mounted thermocouples across the width of the HRSG. And this is beneficial because this is just downstream of the interstage attemperator. So flow here is going, from the back toward the front. This is the gas flow arrow, and it flows up into these tubes. And so one of the things we're looking at with these tube-mounted thermocouples is there overspray that's getting carried into and locally cooling these tubes. So we've got a finite element model, as I've shown, of the headers. And one of the things that we're doing is monitoring these temperature differentials versus time to identify what are the most significant events. So I'll just show, this one plot here shows basically a period of operation. And if I zoom in, you can see this is the one shutdown startup cycle in here. And you can see the top plot is going to be load, the middle plot is metal temperatures, and the bottom plot is going to be the temperature differentials. And I apologize if it's a little bit small, but the temperature differentials are really what we're keying in on to see how the overall header is doing. So you can see during the shutdown, there's a period where some of these tubes are getting shocked down in temperature as this goes on, and that leads to some higher differentials. So I'll zoom in on the next plot, and actually It's all right. I'm just going to switch to the, I've got somewhat of an animation of this. So this is, as I was saying, this temperature plot, you can see right here about 12, 15 or so is kind of when that differential hits. This is then a plot of the temperatures across the width of the HRSG, where the black line divides the left side from the right side, and the green boxes are going to be the inlet areas or the crossovers from that interstage. And if I zoom in here just to around this time, basically you can see, and I can plot this versus time showing kind of what happens to a bunch of these, but what I was trying to get to is the temperature differential is really the tubes on one header are getting cooled more than the other. But if we're looking at tube to tube immediate differences, which is going to drive fatigue damage on these local tube to header welds, those are not as high. So this is, for example, one of the differentials that we're looking at as calculating damage in our models. But there's a bunch more that we could go through, given more time. But the one other one that I just wanted to show real quick is a shutdown from the other unit, which also has kind of similar differentials in those tubes. And if we plot this one up, you can see one of the things that looks like it's happening is, the inlets are at different temperatures compared to the tubes away from the inlet areas. And so this is one of the factors that we're looking at in terms of damage accumulation. So I think, this is a summary of those tubes. I'm going to leave the attemperators and bypasses for a bunch of the other case studies. We'll go through these. So I'm just going to breeze through some of these slides because we'll touch on them later on. But, the one thing I wanted to get to that was a significant result so far from Duke's monitoring is for one of their bypasses, one of the things that we saw is that even though they weren't shutting down and opening the bypass, one of the challenges that one of the units was having is on drops to low load, you see this top megawatt plot. On drops to low load, basically the bypasses, the PRVs would briefly open on those lines, and then the sprays would kick on and they would briefly spray. So you'll see the metal temperatures here basically drop very fast, and you result in a top to bottom difference in the header. And I think on the next slide I show a close-up of this. So zooming in on one of these load changes, you'll see the bottom temperature is basically dropped to saturation temperature, and that'll be this yellow line here is sat temperature. And so you end up with a significant event driving fatigue damage in this header. So this is one of the case studies that we worked through with them that, they're looking at changing control logic on to prevent these cases. But this is just showing kind of the area of the local model we built to that system. And then this is ultimately all the considerations that go into the damage monitoring. But this is kind of the finite element model that we built to calibrate how much damage these events are doing. So we did this for kind of each of their attemperators, and that's kind of the general story. The last thing I wanted to touch on was data quality. So as we implemented their system, one of the challenges in accurately calculating events and damage that we ran into is, how do you know that the TCs are accurately reporting data? So one of the things that we quickly got into is we needed to implement a bunch of data quality checks into the code to detect, are there outliers, are there anomalies in the data, are there constant values, dropouts, thermocouples detaching. And so this is just, for your knowledge, I mean, thermocouples in general are fairly easy to attach, but if you're going to use them for any amount of monitoring and damage calculations, you need to validate that data going in and coming out is good. So certainly it ties together with the initial time classification that I showed, in terms of different operating modes and different transients, because you can then start to do comparisons between units and between tags, sister tags, to see is there statistical differences between, where they're at in different operating modes, how fast they're ramping up. So this is just one plot that we built for the data quality checks showing the same TC across all three units. And so on the left side is a histogram of that temperature sensor, for example. And then the right plot is going to be, a time history showing the three, and they're all mounted in the same spot on three units. So the one thing you quickly see is, this one tag, for example, TE on the blue tag basically is significantly different than the others. So this is a case where there are backup signals on these TCs, and we ended up switching this one to its backup signal because this one became unreliable. And after the switch, it basically jumped back up to here. So there's a couple other examples that in this data quality, aspect that I just wanted to briefly mention. One related to, how good is the temperature sensor in general. So, one of the things that you'll see in this plot on the right, again, comparing three tags on three sister units, and you see a lot of noise in the one signal. So you'll see that, and then you'll also see spikes up to unrealistic temperatures, 2500, 2600. So these are cases that you just have to deal with in the damage monitoring system to flag as potentially bad quality data, and to alert the user, this may be suspect, investigate it. And so one of the things we implemented is a way to discount or remove these events. So that's kind of the damage monitoring system from a very 10,000 view, but hopefully that gave you an idea of some aspects, and the later presentations we'll get into more case studies specific. This was kind of high level. So that's all I had for now. If there's any questions.
Yes. So Bob, are you doing the questions or am I?
Yeah, I'll handle these questions this time.
Okay.
I don't. Go ahead, Barry.
I thought, I was just going to say, I thought there was some 10,000 feet ones that the Kane just mentioned before we get to those specific ones. Do you want to, should we do those?
Sure, yeah, I don't see any in the chat yet, specific questions, so.
Yeah, so I from all the registrations that came in, we had hundreds of questions. So I tried to link them all together. So Kane and Eugene, I'll try to summarize for you. So and I'm not sure there's any specific answers. So the first one from Andre Frager in Brazil is what are the monitoring points recommended for an HRSG? In a peaking and in a flexible power, are they different? And then from another person in Mexico, Armando Farias, how long is required to install this equipment, and what conditions are needed for them? So these are sort of things that Eugene are involved in, that I thought that maybe many people on the meeting would be interested in.
I guess I could start out, Kane, with the first question about peaking versus a cycling plant. And of course, if you're a more base load operation, creep may be more of a concern long term because of you're going to be at higher pressures and higher temperatures for a longer amount of time. Whereas a cycling plant, it's going to be more fatigue related, because then you're going to have large temperature differentials during your startups and your shutdowns. I'd say for the most part, all the equipment you would monitor would be about the same, because you want to account for both, peaking and baseload operation. Anything to add to that, Kane?
Yeah, I was going to say, I think that was a great answer, Eugene. I think that in general, I would agree it's going to be the same components, but it's also going to, the only thing that's going to differentiate is maybe what your budget is for monitoring, where you might prioritize one over the other if you're, slowly building up a program. That would be the main thing. And then there are certain designs out there, any designer will tell you they've gone through and made changes and improvements over the years. So depending on the vintage of your HRSG or your unit, there might be, I guess industry issues that are quick to flag. So I would agree with your general comment. Those are just specific scenarios that might differentiate.
Yeah, that's a great point. Every unit's unique and different too, just with the design. Is it duct fired? Is it not duct fired? What kind of CT do you have? What kind of temperatures are you going to see? A lot of variables and a lot of different factors kind of come into play. I know when we installed our instruments, we reached out to both SI and also EPRI to get a recommendation for which components to monitor, because you can't monitor everything, obviously, so you got to prioritize and you want to pick the highest risk components. So that could very well depend on your design of your unit, your operational profile. So you can certainly tailor that into your specific unit and come up with a list that makes the most sense and prioritize the components. And that's what we did. We worked closely with EPRI. They reviewed our drawings and reviewed the components and kind of gave us a list. And then we bounced that off of structural integrity and they agreed. So that's how we kind of came up with our list of components. And one thing I wanted to mention, to attach the thermocouples, we use the capacitance discharge welding method, the same method you would use if you're doing post-weld heat treat, for example. And we know it's not the most robust attachment technique, versus like a pad weld type of thermocouple. However, you're going to get a very quick response. So we're kind of trading off that, reliability for a quick response and also cost. It's a lot lower cost. But in order to kind of trade off, we added a backup thermocouple to every location. You heard Kane mention we had to swap over to the backup in a couple of situations where the primary might have failed or didn't have a good attachment. So just wanted to mention we built that into our project plan.
Good, thanks, Eugene. Two quick ones which I'll link together. Are there any considerations concerning the age of the HRSG and damage monitoring? And then linked to that, what instrumentation limitations exist and how extensive on a new build unit, and whether you would do it on a new build unit as compared to an old one?
We're actually installing this system on one of the oldest units in our fleet. It's a Neuter Erickson HRSG that went commercial in 2002. And of course, being a different OEM, has a much, they got the reheater in the front, for example, so different configuration, a little bit better access to some of your superheater tubes. That's another factor. You can only get to so many components with the way these are built and how compact they are. So that certainly plays into it, but we're following the same basic process with installing instrumentation and using structural integrity to monitor that, using their plant track data. And as far as the age, it is going to be a little more tricky getting some of the historical data because we have to go back, almost 20 years versus 10 years with this other plant that we're monitoring. So that all kind of factors into it. And then you have to make some assumptions for the components where we haven't added additional instrumentation. So you have to make some assumptions, but you can keep those assumptions on the conservative side. So therefore, you would detect the damage before it fails. Anything to add on that one, Kane? Or?
Yeah, the only thing I was going to say that the other factor in terms of calculating damage on these is if it's an older unit, the material, for example, grade 91 is going to have not as tight of chemistry control. So you might have more cavitation susceptible, type 1 material, as opposed to a newer unit where they're going to have done more additional hardness checks and chemistry, tighter chemistry controls such that hopefully you should end up with better creep-resistant material, but certainly there's always going to be some material factors, and then depending on the age of that unit, and just, you know, the history of analyzing, doing fitness for service, you're going to know some designers, you know, whether they've made upgrades over the years that might not have got implemented. So, you know, Wes can maybe talk a bit more about that in his presentation too.
Thanks, thanks, Kane. Go ahead, Bob, with the others now. I think
Yeah, there's a few questions that have come in on the chat. So David Anderson asks, besides utilizing the data to drive end-of-life inspection planning, will the information be used to drive intermediate maintenance approach and parts planning and stocking decisions?
Yeah, I mean, from our
Okay.
perspective, I was going to say, at least, you know, for the inspections that we know, you know, Duke has done on their attemperators, it's always been a challenge of if you do an inspection once and you find damage, then you often whoever did the inspection is going to recommend a very short interval. Whereas if you've got those TCs to recommend and to monitor, basically, you know, are there significant events still happening after the fact, whether you've tested nozzles, replaced valves, etc., then so it allows you to make those proactive decisions on just maintenance related activities. So there's one presentation in particular, or one case study I meant coming up where, you know, there's a throttling valve on a temperator, and it's something they know they have to do regular maintenance on. And so, you know, having those differentials monitored versus time, they can see when they start needing to do a rebuild on that valve, basically.
Yeah, anytime you can find issues before an outage instead of during an outage, when you have to scramble and get parts, you know, rushed in and try to find things last minute, that's a huge benefit to go ahead and have those, you know, parts on hand when you see that something's starting to degrade and you suspect it could be an attemperator nozzle or, you know, a valve. You can go ahead and plan for that early.
Yeah, the one last thing I'd add to this that I was thinking about, just fitness for service perspective, you know, if you go into an outage and you find damage, often if you don't have that component on the shelf, we get asked the question a lot, can I run till, you know, next year or 2 years to my next major? And if you've got the monitoring data, it dramatically accelerates, you know, the fitness for service and the confidence you can have that whether or not you can run that long. So we often run into cases where we get asked that question, but you have no local temperature data, and we're kind of making assumptions, and you just don't have as much confidence in the future reliability decisions.
Good. Daniel Larson asks, does SI have criteria for different types of cycles for each area of the HRSG?
Yeah, so there's definitely different, and even between different manufacturers, there's different cycles. So often each manufacturer will design or qualify cycles in a different way, and your unit may count hot, warm, and cold cycles. For us, we're generally going to be concerned mostly with the local transients and operating conditions, and you know, a lot of what we're integrating into PlantTrack is doing pattern recognition to quickly identify those different events when they're happening on a component specific level, as opposed to just, hey, my CT did this. So the short answer is yes. I think it's component specific.
Okay. Nick asks, why did the HV bypass valve, when dropping low load, spray? Is it supposed to do that, or is something wrong?
Yeah, there's definitely something wrong. So these units don't require ammonia spray, and so we've been able to push the loads extremely low, and that's helping us to prevent the units from cycling. So we've been able to go all the way down to 40 megawatts per combustion turbine. So the total, you know, plant output somewhere around what 250 or so megawatts, which really helps us to manage the solar. So we'll turn down these units daily during the peak solar output around 3 in the afternoon, and instead of having to cycle them on and off. So that's been a big part of our flexibility initiatives. But for some reason, the way the control logic's set up, when we get into these really low load operations, that unit Charlie hot reheat bypass pressure control valve wants to pop open and spray into the system when obviously it's not needed. The system's still online. Bypass valves are really designed for startups and shutdowns and unit trips and things like that. So it should not be opening during normal operation. So we discovered this because of the damage monitoring system. It alerted us that this was going on, and we are looking into the control logic currently, and there's some outstanding action items to resolve that issue and correct it. So hopefully that answers the question.
Yeah, that good. Nick has a quick follow-up. Do you also have monitoring on the cold reheat or the hot reheat bypass? No, I'm sorry. I'm reading the question wrong. Yeah, Nick, this is on the HP bypass to the cold reheat, this case study that we're talking about now. And he asked, is there a drain pot on that pipe? And I think the answer is probably no.
So we do have drain pots. I'd have to look at the PNID to see if there's one. Are you talking about between the hot
On
reheat
that
bypass and the
bypass line, I
condenser?
don't think so.
Yeah.
It would
Good
be
question.
unusual to have one in that line.
Yeah.
Doesn't look like it. Okay, that's it for now. So
Okay. Thank you.
thank you.
Good.
Scott, Bob, we good to go?
Yes.
Alrighty. So welcome everyone. Eugene, Kane, thanks for that first presentation. Very informative. So we'll get started. So my name is Jacob Boyd. I'm from St. Charles Energy Center here in Waldorf, Maryland. We were commissioned in 2017. We're a GE unit with .05s with the DLN upgrade, along with the D11A steam turbine, and our HRSG is CMI. So our units cycle quite often every year, anywhere from 140 to 170 cycles per year. So this presentation is similar but different to Eugene's. So Eugene, then we're monitoring the HRSGs. Since we cycle, we're monitoring our attemperation and desuperheaters. So why? So like I said, 2017, the plant was commissioned. In 2019, the plant experienced a through-wall leak during a cycle event. Luckily, we were able to get online and get vacuum, and we were able to stay online for about, I want to say, 18 hours to get everything in place to actually make the repair. So the site was concerned. 2 years after commissioning, we already have a through-wall girth weld crack, as you can see in this picture below. We contacted Structural Integrity. I was able to send the material sample down to their lab in Texas. The root cause from their lab, thermal fatigue. So we worked with Structural Integrity right after that to install local thermocouples. This is just the beginning of the process to monitor the spray. So fast forward. So the original plan was just to install on the hot reheat bypass of the failed girth weld, which is unit 12. So within 30 days of installing these local thermocouples, we saw temperature variations up to 700 degrees. This concerned us, so we contacted our bypass valve manufacturer to talk about a redesign of the nozzle or the lands, depending on who you're talking to. So we were able to modify the lance and replace that in 2020. So after we had the local thermocouples installed and found that we needed to redesign our lance for unit 12, we decided to go forward with Structural Integrity to do additional monitoring on our AGP issues that we could find during regular inspections. Working with Structural Integrity, we were able to install the wireless monitoring system similar to what Eugene and Duke Energy installed. So I'm going to breeze over this right now. If you have specific questions on risk ranking, this is going to be after the conversation towards Kane and Wes. This is how they rank piping systems and what we should be monitoring. It takes into account multiple factors. And like I said, this is more of a structural integrity question. So how do we get the data? So our plant, we did not put the data into our DCS just for cost reasons. So structural integrity was able to get, they provide these data collection nodes, which you can hook up multiple sensors and multiple thermocouples to this, and it transmits back into your plant track website specific for your site. So as you can see, this is an actual installation of one of the data collection nodes. Very small. It's not in the way of our maintenance guys. The one thing you should be considerate of is the wires going to and from the node. You need to make sure they're bundled nice and neat so nobody trips over them in the plant. So this is more or less a cybersecurity image of how our data is transmitted. So I don't know if anybody on this call is in charge of their SIP compliance for their local region. I am. So we do not have this go to our OT server. We have it separate into our IT. So that kind of saves us. However, it's still in our OT procedures for SIP to make sure we have firewall and it's protected as best it can be. So email notifications. This is what I like. This is my favorite part of structural integrity's solution. So I'm the only engineer at this site, so I have a lot of different things going on. I don't have time to review pod data every day of certain reheat attemperator loops or bypass loops to see if we have temperature differentials. The good thing is structural integrity, when they set up the solution, you sit down with them and tell them and have a discussion of what you consider a low, a medium, and a high impact alert. So I put a snippet of one from our site. So as you can see, and this is real time, so when we start up at 4 in the morning or 7, they come through if there's a temperature difference event. So as you can see on this one, we have HRSG 12 reheat attemperator loop. What's the event? There's a temperature differential. Okay, how much? 112 degrees. So it's a low criticality. Then it also provides a count if you cycle a lot like our site does. In the last 7 days, how many temperature differential events have we had? So in this case, we've only had one. So is it a one-off or is this something we need to dig into more? So once the solution and the PO was cut to structural integrity, out of 25 piping systems at our site, we have a online monitoring tool on 10 different locations for piping. We also have pipe hanger locations, which will be discussed, I believe, in this next slide. Yes. So this was a request after the HRSG form. People wanted to know a little bit more about the pipe monitoring. So this one you see here is at our actual facility. This is on our Unit 11 hot reheat to the steam turbine. As you can see, you have your data collection node here. You have support mount, then you have the, I'll just call it a string, but hooked up to your support, and it tracks during normal operations. So just for some reference, I included what our site sees on this specific hanger in plant track. So as you can see, this is normal operation starting from 10/15/2023 to 11/28. I know it's only 11/7, but I just went ahead and put 11/28. We're sampling at 5-minute frequency, and this can be changed to seconds or minutes. So here you can see where I was actually doing a pipe hanger walk down. I actually pulled the string to make sure it's reading and can see things. So normal operation, then you can see we've been cycling some. And this is the kind of data. You can download the data in the upper right into an Excel spreadsheet and compare it against load, pipe temperature, etc., whatever you prefer. So a little bit more on the plant track system side. So this is a database for our site. So you don't have to keep internal files if you don't want. Everything is held within here. So I have it broken up. You can set this up any way you want. You can talk with the structural integrity developers of how you want this set up. So you can see we have it separated, unit 11, unit 12, high pressure, hot reheat, then there's cold reheat too. You can see in our projects, we've had a 2022 monitoring assessment, HEP inspection in 2023, a cold walk down and a hot walk down. So all the data is right there. The other good thing is you can dial in. Okay, so I want to look during our last failure was the unit 12 hot reheat bypass. Okay, so I want to look at our, let's say, monitoring locations. Then I didn't put the image, but you have images of exactly what you're looking at. Of any defects, any reports can come to this attachment here, so it's for quick reference. Then I believe Eugene kind of showed this earlier. Structural integrity makes a nice 3D model of the actual piping system and labels all your pipe fittings, supports, your welds. Then you can also see where the support inspection was and the weld inspections. Very user friendly. Okay, so fast forward, 2023 outage. So we were seeing temperature impingement events at our hot reheat bypass number 12 again, even after the Lance redesign. As you can see in our online monitoring, we've had 5 high events and a total of 155 medium events. So it was enough to go in there and actually do NDT. So just for reference, this is a 26-inch, 3/4 inch thick wall. It's P11 material welded to a P11 bore valve. So during the inspection, there was cracking found on the circumferential positions all the way around. The largest position was at the 6 o'clock with 4/10 of an inch deep in terms of cracking. So this caused our site to replace the pipe in its entirety with a 7-foot spool piece. So here are some additional inspection pictures of our cracking. This is the interior at the 6 o'clock position. So just a little bit more on that crack. Still thermal fatigue. Our site's currently working with our condenser vendor and the bypass valve vendor to see if we can modify the control logic and how much heat we can actually dump into the condenser, along with inspecting our block and control valves. However, in short, for me, this project's been super valuable. It has saved me time. It saved me digging through drawings. It saved me from spending a whole day or week looking at PI data. The other good thing is Structural Integrity has engineers that if you reach out to them, say, hey, I saw this, what do you think? So that's one of the other beneficial tools. So I think I'm up on my time, but if you have any questions, just put them in the chat and I'm sure Bob or Barry will let me know.
Yes.
Okay,
Okay.
very good.
So
Yeah, there are
Scott,
no
we don't have,
questions.
oh, go ahead. Sorry, Bob.
I'm sorry, yeah, there's nothing in the chat at this point, Jacob.
If you don't mind, I would like to ask Eugene a question.
Please, Eugene, you still here?
Yes. Yeah, go ahead.
So Eugene, on that bypass valve that you had opening up, are you doing internal control logic or are you having a third party guy kind of take a look at that?
We have a very good internal DCS engineer, and yeah, he's working with the plan. I think they've already marked up the control logic. They've tested it on the simulator, so now it's just to have to install it on the real thing. So yeah, he's done the kind of the review of the logic. I can't speak to exactly what was wrong. I'd have to reach out to him. I just know he's been working with them to resolve that issue.
Gotcha.
Yeah.
Yeah.
Eugene, I'd like to waste 2 minutes and ask you another question about that. Was the pressure control valve also opening, or was just the spray valve opening on that?
It was
bypass?
both. Yeah, so the hot reheat bypass pressure control valve would pop open, randomly during these low load
Yeah.
conditions, and we were seeing very high differentials. Kane could probably correct me, but over 400 degrees on some of these events, and very large differentials, very damaging. And then, of course, you
Right.
got your spray valve that opens in conjunction with the pressure
Right.
control valve.
Okay, great. All right, thanks. Don't want to
There's
take
a
more
question,
time from this.
there's a question from Julio, Bob. It's a question for Eugene. He just wants you to repeat how you attach the thermocouples using the capacity welding technique that you mentioned very quickly.
Yes, so there's very specific instructions. So I actually worked with Bob Anderson when we did our first round of attaching tube skin thermocouples at one of our power plants, and he really helped out, him and EPRI as well. They have some reports that actually show you photos and show you the attachment techniques, but it's a capacitance discharge welding, and it's just a small unit that's battery powered that you can take in, and you prep the tube, and then they're able to kind of zap them on using this this technique. And then the way you route the thermocouple wire, and you wrap it with insulation, you secure it with tie wire, and then the type of thermocouple wire you use is all specified in there. And we just used type K thermocouple wire that has a fiberglass sheath with a stainless steel outer braid, and that it's made to withstand the high temperatures you'll see in HRSG. I think it's rated for up to 13 or 1400 degrees, and it does well. It's as long as you attach it properly and leave a little bit of room for thermal expansion, it's gonna last you many years.
Yeah, Julio, if you want to drop me an email or through Scott, send a message, I can send you those details. It's not very complicated. There's a few key steps that have to be done, but it's not expensive or doesn't take a horrendous amount of skill.
Yeah, and
Is
also wanted to mention that you don't have to do the post weld heat treatment, even if you attach to a grade 91 tube. The code allows you, as long as you meet certain requirements and have certain energy levels or less, you don't have to do the post weld heat treatment or preheat. So that really helps things when you're attaching to grade 91 components.
And are any, Eugene, are any of these done with pad weld? That's what we always used to use in the fossil plants. I thought I saw some of those in one of the presentations.
So we chose not to do the pad welds or the little disc. After consulting with Bob, we felt like the quick response would be more important than the
Yes.
better attachment technique. So that's what we were looking for, was kind of that quick response from the like when you put in a big pad weld, you got all that thermal inertia, and you'll get a slower response if you got a quench or a slug of water.
Yeah. Plus, and since a lot of this is on P91 material, now you're stuck with post-weld heat treating, and the cost would probably go up by 10 to get involved in that.
Great point. Yep.
So there's
a hand. Excuse me, Bear. Go ahead.
I was just going to, as there was no more questions in the chat, there was a couple in the questions that we received.
There's one hand up. Ray Dio has a hand up. Scott, can you unmute Ray?
What was that? I didn't see that.
Yeah.
Can you guys hear me?
Ray Doyoy.
Yeah. I don't hear anybody. Are you there, Ray? All right, Barry, go ahead. Apparently, this isn't
Was
working.
it, this was the question that came in from Ori Seltzer from IMI, and he probably is asking Kane. He wanted to try to understand a little bit the challenges of tag mapping the sensors, and whether SI is providing any physics-based real-time calculations.
So at that point, I guess there's two questions there. So the physics base is really relating basically what is happening to, I mean, that's where we're using the damage calculations. So I guess it depends on which one you're talking about. So certainly for the creep damage, those pull in the pressures and temperatures and put them into an appropriate creep life correlation. And the stress is determined from previous redistributed analyses. The fatigue damage then is calculated, basically there's a couple different methods that we've implemented over time. So the very first iteration was we ran the representative transients and determined how much, stress and strain we got from those and related that to damage as a simple lookup table. So that wasn't the real time. What we've gotten to now is building out, basically Green's functions related to that, more real time tie the temperature and pressure to a direct stress and strain. And so that's certainly what we're implementing for Duke. But then I guess the other level that we've worked on as well, which isn't part of monitoring yet, although I see it in the future, is somewhat, some people would call it a digital twin, where there is actually a finite element model running real time that, takes the input data and uses that. So there's a couple different levels. Yes, we are using it in physics-based models, but I don't know if I answered all of Marie's questions.
Yeah. Yeah, that's good. Yeah, that's great, Bob. There's two on the chat here.
Yep, Mike Oatley is asking, I think this is for Jacob, since you didn't put the monitoring data into Pi, is it difficult to prepare data from both systems, line up the times and so forth?
It does take some time, but it's not overly cumbersome. I think it took me maybe 3 or 4 hours to do that, to do the comparison.
Yeah, and you only do that when you're trying to run down a problem that it flagged for you, correct?
That is correct.
Yeah, okay. The final question from Thane Wade is the capacitive discharge welding restricted to piping of a specific material? No, we have done the years ago, we did the lab work and got the approval of all of the HRSG manufacturers at the time, even under warranty, to use this technique on any material on the tubes, headers, piping, and so forth. So it's a very low energy. And as Eugene said, there's not enough energy to require post-well heat treat, even on PET 91 materials. It's basically the same technique you see the post-well heat treat contractors use when they spot weld thermocouples onto the part that they are heat treating. We just make it a little more robust by the way we tie down, insulate, and put expansion loop in the wire.
Bob, I have one. We have one more question here. This is from Charles Turner in Canada. Kane, can the technology be applied to midlife facility? I think you've already answered that. And how has the technology been validated for CSEF steels?
Yeah, so certainly you can implement it midlife. I would say most people are at that point of implementing it midlife. The challenge is always doing the backward. How much damage did we accumulate prior to, or what events might we have had previously? And there's always going to be some level of uncertainty there. That's why we try to pair stuff with inspections. But I mean, certainly getting monitoring installed is going to give you a lot of value on its own going forward to identify when you're having events. So it can be midlife cycle, and then I'm sorry, I forgot the second half of that question.
But whether the overall technology had been validated for CSEF steels, Kane?
Oh yeah, so certainly, we're using, the latest, uh, material correlations for creep life and yeah, I don't think there's any challenge with implementing that. I mean, some of the differences or challenges in creep stress strength enhanced veridics are going to be how accurate do you want to get. So a lot of what we're doing is somewhat Robinson's rules calculations using creep redistributed stresses and adjusting it for operating data. But there's always, you can sharpen the pencil. I don't think there's anything wrong with the material correlations for the CSEF
Yeah.
materials.
Yeah. One last chat, Bob.
Yeah, well, let's see, Ray has his hand up again, so let's try again to get Ray on here.
Hopefully that works now. That
I
work?
hear you.
Oh, good. Now, I was just curious as to the cost of this system that you implemented for monitoring and gathering all this data. I mean, is this a $20,000, $200,000, or $1 million to do all the what you've done here?
Okay, pick A, B, or C there. That's about as close as we dare get to talk about pricing.
Yeah.
So,
Kane, if you, this is Matt Freeman from Structural Integrity, and I'll just share from our side, Structural Integrity providing it, and I know, that the host utility has some additional costs to set this up, but it really depends on the number of locations you want to monitor. If you were just monitoring an individual temperature, that could be set up in the tens of thousands. I would say 20,000, to set it up, and then there's an annual fee to keep that going. But if you wanted to, monitor up to 15 locations, it could get into a couple 100,000 as well, depending on just how much you wanted to do monitoring for. So I guess the answer is there's a wide range.
okay. We have one more question from Ralph McBride. He's asking, how are the wireless transmitter powered? Is there a central power supply for each?
So Kane, or do you want me to take it? So our site uses solar panels on each one, but I believe Structural Integrity has some new technology to where it's battery powered. I don't know if Kane or somebody from Structural Integrity can field that question.
Yeah, so certainly, I don't know if the battery powered ones are off the shelf right now. I can check with Jason. I mean, there are the ones where we plug it into an outlet and it's got a battery backup that will run. Same with the solar powered ones. There was, discussion of there's another technique basically that uses the heat of the pipe to basically recharge the the nodes and gateways, but I don't believe that those are fully operational. I'll message the our instrumentation team and I can reply back.
Yeah, but in short, the St. Charles site uses solar panels and we haven't had any issues.
Oh, actually, so they already responded to me. He says battery power only. So going
Good.
forward, yeah.
Okay.
Let's move to the next one.
Yep.
Part. Wes, are you ready?
We're getting Wes set up here, but if you want to field that last question that came in, Bob.
Yeah, okay. Percy asked, could you share the tables for active tracking of the temperature? I'm not quite sure what that means. Kane, maybe you know.
I don't know which specific tables.
Maybe you can unmute Percy if you can, Scott, and we'll see. Maybe you can expand on that question.
Okay, he's unmuted.
Okay. Percy, you want to ask your question? Hello? Maybe he doesn't have a microphone.
Yes, it's a P19.
Yeah, we can hear you. Go ahead.
19.
I think he wants the P90.
P90. Let me.
I don't understand the question. I'm sorry.
I can't see it, so.
Yeah. Percy, maybe you could, write a little more expansive question in the chat, and then we'll loop back to it later, so we don't hold up this other presentation. Are you ready, Wes?
I think so. Let's can okay. Can you see the see my
Yep.
presentation?
Yep,
Yes.
it looks good.
It's
Okay,
fine.
good. Okay. So I think a lot of discussion you just had covered some of the first things that I was going to talk about. But this is a picture of the spot welded thermocouples on one of our test sites. And I think
Wes, we don't see a picture.
you don't see a picture.
I see your title page. But maybe that's not you. Maybe that's Scott's summary page.
Okay, you don't see case one?
No,
No,
can you minimize that, the presentation that you have up? We've got your presentation on the WebEx screen. So if you click on the little green and blue W down at the bottom.
Green. Okay, did that do it?
Can you advance the slide?
All right. Oh, I guess I'm not looking at the right thing here.
I think if Scott or Kane, if you have the slides, maybe one of you share. That way.
Yeah, I mean, I could just share my screen, Scott, if that's easier.
I just passed that over to you.
Okay, that's good. Okay, yeah, so I have control now.
well, we had it. There we go.
Yep.
Okay.
Wes, I can just advance the slides whenever you're ready.
Okay,
You can
good,
see this.
good. All right. So, right, so jumping back. So these are pictures of actual spot welded thermocouples at one of our installations. I think the previous discussion pretty well covered the use of those. Just a comment on the use of these or being safe to use on the grade 91. Back when I was with an OEM, we actually sectioned up a section of spiral fin welded 91 tubing to look at the depth of the weld of the fin to the tube. And obviously those are not post-weld heat treated, and that the depth of that weld is much, much deeper than you'd see on the spot welds here. But looking at this is a hot reheat bypass, and you can see this is fairly typical of a lot of these where you've got a very, very large change in diameter, wall thickness, and probably material combined with a 90-degree valve. So it's not, you've got stress concentrations due to all those things, and then usually a lot of flow issues. So it's not surprising that you're going to have issues on these. So next slide. So this is some of the operational data for that unit. We've got thermocouples located at the quarter points, essentially 12, 3, 6, and 9 o'clock around that pipe. And again, what you see, not a surprise, is that every time this unit starts up or shuts down, you're getting an event where you're getting a rapid change in temperatures. And you'll also see in the next slide that there's actually a lot of spatial difference around these pipes. So you're getting two types of stress. Yeah, go ahead. Go to the next one. That's good. Two types of stress to be concerned about. You get the rapid temperature increase as well as the non-uniform temperatures around the pipe. And this shows both the thermocouples data and also the plant operational data. So you can see the steam temperature out of the bypass is from the thermal wells that are located well downstream of the bypass, and the thermocouples are the ones that are very close. So if you're just relying on the plant instrumentation, you're going to miss considerably the peak temperature spike that occurs, and you're not going to get any information on the temperature distribution around the pipe. And as you can see, you typically think the worst temperature is top to bottom, but in this case it was not. It was actually between the 12 o'clock, which is the top of the pipe, and the 9 o'clock, which is one of the sides, where you ended up with about a 400-degree local temperature distribution around that section. So this shows the need to originally, when we started doing this, we were just putting top and bottom thermocouples on way back when, and we added the thermocouples at the quarter points, and it shows us that if you only put them on the top and bottom, you're often going to miss the most of the worst temperature variations around the pipe. Let's see, go ahead, next one. So this is another hot. Well, actually, this is an HP to cold reheat bypass, and the thing that I wanted to point out on this one is that these thermocouples are downstream of the bypass valve, yet they are cooking along at 800 degrees before that bypass opens. So this monitoring is not only showing, well, what it's showing, I believe, in this instance, is that you got leakage through that bypass valve, because looking at a sister unit, we were seeing temperatures about 200 degrees, which is what you'd expect from a line that has no flow in it for a while. So the monitoring system, besides pointing out excursions and variations, it can also give you other interesting information, such as this, that your valves are leaking. And I've seen this on several units where you expected to have your pipes sitting at ambient, and they're running much, much hotter. And the far downstream thermocouples, the thermal wells, could be hundreds of feet away from the valve, so that even if you got some bypassing steam, by the time it gets down there, a lot of it is cooled off, so you're not really getting the good feel for that with your plant instrumentation. Go ahead. Yeah. This is a thermocouple arrangement on a attemperator, an interstage attemperator, and this is, I'd say, so typical of earlier units where there's definitely not enough downstream distance between the sprays and the downstream elbow. So getting spray impingement on that downstream elbow is, I'd say, not unexpected if you don't, well, for a lot of reasons. So on any installation like this, we'd be putting thermocouples on that downstream elbow to look for impingement. And we also are putting them downstream of the spray station itself, on the pipe itself, again at the quarter points. And because you see often that there's spray impingement on the pipe for a variety of reasons, leaking valves, spraying to saturation, broken nozzles. So when a unit has a liner such as this, we put the thermocouples one diameter downstream of the liner. If there's no liner, what we would typically do is put a set of thermocouples about 1 diameter downstream of the sprays, and then preferably like another 5 diameters downstream of the sprays. We put a second set so we make sure to catch the worst of the impingement. Let's see. And let's see, keep going. Next slide, Kane.
Yeah, the one thing I was going to say about this though, Wes, just real quick while we had it up, I thought about it, and this was the question came up before. You know, what was one difference between the designers and a change that was made over the years on something you account for in monitoring, and a lot of these units flow comes from the top side here and flows around and goes out the inlet on the bottom of this pipe, but then the attemperator right now is on the upstream side of that U-bend. And there was a previous design, where the attemperator was just upstream of it was on the downstream side of the U-bend. And often what that led to is, spray water making it into those tubes immediately downstream. So I just realized that this was a good case study of, why some designs have changed over the years as well to give you, it's still not great having a U-bend. So.
Right. Even if you have the attemperator sprays downstream of that elbow, usually there's never enough upstream distance between that elbow. People worry about the downstream distance, but the upstream distance of sprays is also important because, as you'd expect, the flow coming around that elbow is all piled up on one side of the pipe. So if you have sprays that are too close to that elbow, too close to the upstream elbow, that non-uniform steam coming into the sprays, even if the sprays are uniform, which is in itself, questionable, that non-uniform steam flow is going to push that spray up to one side or the other. So, adequate upstream and downstream length are important. And it's, I think finally people are starting to do that in their designs, but historically that was not the case. Okay, so move on. So this is data from one of 2 sister units on a 2-on-1 unit, and you're looking at temperature differences from the thermocouples in a range of plus or minus 80 degrees Fahrenheit. You've seen negative temperature differences in the bottom because you're looking at the extrados minus the intrados, so you're slightly cooler on the outside, the inside, so that negative becomes a negative number. But everything, not something to be terribly concerned about with a temperature total difference in that range. But when we went to the next unit, which, can you go to the next one? This is what we started seeing, temperature differences 300, 400 degrees Fahrenheit. And the first question is, wow, is this real? But when you start looking at it, you see that the trends are consistent. Your temperature differences top to bottom on the pipe and intrados to extrados and top to bottom on the elbow are all consistent. So that, it's not a question if you had 1 or 2 bad thermocouples, you wouldn't expect that everything lines up together. And this is concerning to see this large a temperature difference and to see it continually happening. So as I think either Jacob or somebody else mentioned, we get notifications whenever this happens. So we started seeing this on a regular basis and contacted the plant operators and made them aware that we're seeing this, and they decided it was worth looking into this in more detail to try and understand why one unit is looking so bad compared to the other one. So we started delving into their operating data. Now these units had an inspection in 2020 and didn't see anything, and the thermocouples didn't go in until 2023 this year. So so we didn't have thermocouple data to look back at. So we only had plant data to go through, which we started doing. And you go to the next one, Kane. So, and what we saw is that the steam temperatures entering the unit 2 hot reheat attemperator are consistently higher than the temperatures coming into the unit 1, which has had the smaller temperature changes, and the temperatures coming out of unit 2 are lower. So you're spraying higher, coming in hotter, spraying more on unit 2. So the next question is, why is that? Yeah, go ahead to and so, yeah, we historically went back and looked at spray flows, and this is normalized to similar same operating conditions. So we only looked at data for comparison when both units were at the same operating conditions, and what we're seeing is that the spray has been consistently higher on unit 2 than unit 1 starting in 2001, and that the spray has been increasing since 2000. So although there was an inspection done in 2020, not 2000, and nothing was found, there is some concern here because looking at these sprays, although we don't have thermocouple data, you can infer that they've probably been doing this for a while. And then starting looking at more plant data to try and get a better understanding why this unit's spraying higher. Go to the next one. Among other things, we looked at the cold reheat steam flow into each unit, and unit 2 has consistently lower cold reheat coming in than unit 1. And we looked at the other operating parameters, and looking at the reheat section directly upstream of the attemperator, there were some thermocouples in the gas side, so we could check and see that the gas temperature coming in to that heat exchanger upstream of the attemperator was essentially the same on both units. So, with a simple heat balance, you figure that if you got the same energy coming in when you've got less fluid in that, you're going to get a higher heat pickup. So this was the discussion that we had with the operator, and they're presently looking into this now to try and get an understanding of can they rebalance their cold reheat to hopefully even things out between the two units. And let's see, keep going. Okay. And this is something that was alluded to a little bit earlier also. This is a plant track history of events for which we and the plant operator would get notifications of. And this is very helpful because over time it allows you to see, A, do I have a lot of events, and B, am I suddenly getting a whole cluster, which we're seeing here, and then you can go in and look at it. So this circles back to, looking at this large number of events on the right here. This is for a bypass, not for that other unit, but the same thing is this is where we would begin the discussion with the operators on, you've got something going on here that needs to be looked at, and which would lead to the further studies. And Kane, I think next one is something you can take.
Yeah, I'll briefly go over these. There's 2 case studies left, but I can do them quick. So the one case study is also another HP to cold reheat bypass. So you can see this is actually a unit where they had installed temperature sensors on the downstream elbow many years ago. So they didn't have anything immediately out at the outlet of the bypass attemperator, but they had them at the downstream elbow, and they've had a number of problems with thermal fatigue cracking where the HP line ties into the cold reheat, which is down on the left side where you see some of those instrumentation. So the one thing that we did for this plant is looking into some of their data, just from the limited temperature data that they do have on those downstream sections. You can see they're getting still a differential there. Even I guess just jumping back, these two temperature sensors are on opposite sides of this last elbow, so it's giving you basically a left to right and upstream to downstream combined differential or difference. So when they operate that bypass, though, you are seeing a differential, which if you're seeing it there, that's where the question begs, how large of a differential am I seeing further upstream as well at the outlet of the attemperator? So, this is one thing that we basically did since they had a longer history of this data, and they had a history of maintenance that they were looking at as well. So for each of their startup cycles since unit commissioning, we basically went in and we said, okay, what is the peak differential from this hot, warm, or cold start? So as an example, this is a warm startup cycle from 2021, where the max differential here is going to be this 170 degrees. So if we plot that versus time, I'm just going to jump to this slide. Then you can see just each one of these dots is as a startup on either the Unit 6 or Unit 7 bypass. And what you see pretty quickly is, okay, after 2016, Unit 6 has a lot larger events. They're frequently greater than 200 degrees. Unit 7 is a little bit lower. They actually did an outage here in 2017 mid-year. So that's where you'll see the drop off in data. And during that outage, they rebuilt their throttle control valve for the spray water line itself. So after they did that, you can actually see, the number of the magnitude of differentials that they're getting at that downstream elbow is significantly smaller. We're down less than 100 degrees. So unfortunately, then we get to 2019, and one of the temperature elements stops working. It stops recording data whatsoever. So there's a period where you were getting nothing. When they finally fixed that after an outage, all of a sudden you see, Unit 6 is way back up again. And actually, if you look at the trend, there's some points in Unit 7 that are also trending up. So one of the things they did in kind of continuing on in this data is actually, this plant knew that they were having problems with the throttle control valve, basically on that spray water line. So they ended up replacing nozzles as well as rebuilding that throttle control valve. And then they even installed a second set that on their own volition. They kind of decided, we don't trust this throttle control valve, so we'll put in a second one with a drain in between the two, so that if one fails, the drain is opened up and any spray water that would leak by leaks into the drain and not into our main run, causing a larger differential. So certainly there's this plant is still installing additional instrumentation to try and to more accurately determine what exactly is going on and what leads to these differentials on startups. But just from having a limited set provided them valuable data to see a trend in these differentials that would drive damage. So the last case that I just wanted to talk about is this is another case of a temperator malfunction that you can see, where the spray water valve, basically well, you don't see the valve position here, but the throttle valve basically was, when the bypass is operated, it's trying to seek out the right amount of spray water to let in. And so the control logic is constantly adjusting that throttle control valve. And what you see then is at the downstream bypass temperature, it's going up, down, pretty quick cycling. And so one of the things you're looking at is how damaging is this, and because these temperature swings are so small, they're, I shouldn't say so small, they're still on the order of 50 degrees or so, but uh, they're not as damaging as like, spraying down to saturation temperature. So it's something that should get fixed. But I think that's where, trying to tie in that physics-based model to help quantify what the damage is from these. And some of these cycles are so fast. The challenge with the valve hunting is the metal temperature, because it has that thermal initial inertia, so it doesn't always have time to respond. So if you're looking at, quantifying damage, these are something that can be fixed by adjusting control logic. But that's where I guess it's helpful to identify these, and then the next step is quantify how much damage they may have caused is helpful for prioritizing how soon do you need to get in there and do an inspection again. So I think that was the last kind of case example that we had put together. I just put up the last couple reasons on why we think it's beneficial for people to do monitoring. And I'm not, this isn't at all a sales pitch. I found tremendous value in having additional data from plants to be able to identify what their issues are, and I found it extremely helpful in making recommendations, extending fitness for service intervals, and to me it all ties together into just improving the confidence in your unit reliability. Just having more data, the better. And I think the trend in monitoring is going to continue, where we talked a lot today about temperature sensors, but there certainly are other sensors that are out there on ultrasonic sensors for spray lines to monitor flow through them, and to put on drains to see if all your condensate has come out of the system. And the other one that we've certainly been working on is installing sprayed on transducers to either actively monitor thickness on components where you're worried about a corrosion issue, or installing spray on transducers in an area where you're expecting damage to one day do LPA focused monitoring and check if you're getting an active crack. So that's just where I see the kind of future, and I find it extremely helpful. That's kind of all I had. If there's any questions for Wes and I.
Good, thank you.
None in the
Bauver.
chat yet. Barry, do you have any additional ones there?
I don't see anything in the chat, and
Yeah.
there's let me see, there's not really any questions from the registration either.
Yeah.
Any general
well,
ones.
Okay, if
But-
anyone has here comes a question. All right. Not surprisingly, Kane, you mentioned spray-on transducers, and we have a question from Ralph McBride. What the heck are you talking about?
Gotcha.
That's not what he said, but that's my interpretation.
Yeah, actually, I mean, I can talk a bit about it, but Scott, if Robert Chambers is in the chat, I think he would be the best one from our side to talk about it real quick.
So he says,
Hey.
is that strain? You mentioned a couple other things as well, I think.
Yeah, I mean, certainly, one of the ones is ultrasonic sensors to put on spray lines. And Eugene, I think you can probably talk. Well, if he's still on, he could talk to the fact that
You mentioned spray on transducers rather than
Okay.
transducers on spray lines. So are you actually spraying some kind of transducer for real-time monitoring on a component?
Yeah,
As opposed
so maybe I confuse things by mentioning spray. So there's ultrasonic sensors that you could put on the water line to detect that there's
Yes.
flow going through it. That's one type of ultrasonic sensor for spray water. There's
Right.
also a spray-on transducer, which basically you can think of it, like an ultrasonic thickness meter But when I say spray on, you're actually basically applying a piezoelectric paint to the piping that you can connect wires to, and you can actively monitor thickness during, real-time operation. So they're somewhat different, different
Yeah,
than,
yeah. Well, okay. So the spray on, that's a ready for prime time product at this point?
yeah, I mean, definitely I've got another slide in a different presentation, but for a different plant, we've been monitoring with spray-on transducers for 3+ years now, I'll say. And certainly what we're working towards is the linear phased array approach to eventually one day be able to monitor cracks. So the limitation on those is temperature right now. So, if it's below 800 degrees, we can accurately monitor real-time temperature or real-time thickness data. Once you get above 800, the challenge with the spray-on transducers is, you get an oxidation layer that forms that often adds additional, noise to your signal. So,
I see. Yeah, Robert Chambers is unmuted. Robert, do you have something to contribute there?
I think Kane covered it pretty well. I mean, it's basically what he said was it's a kind of a permanent install of ultrasonic transducer right onto the pipe, and yeah, the challenge at higher temperatures above 800 that we've seen, it's oxidation issues. The sensors certainly operate above those temperatures, but they won't last as long. So I mean, we're actively working on that, but yeah, that's about it.
So what kind of locations are you putting them in? Are you putting them in like hairpin bins and economizers, or are you just putting them on pipes, or what?
So the one case that Kane mentioned, we installed some on elbows on the desuperheater drain lines that in the past they were experiencing erosion. So we're basically just looking over time at the wall loss on those elbows. And we've identified about like 28 thousandths wall loss on one of the elbows at over a 3-year period.
Do you think on a evaporator riser or tube bins in an economizer, this would be applicable?
I'm
I'm
not
thinking
as
FAC for monitoring FAC progression or damage.
I would
yeah,
definitely.
it could potentially be an option there. I'm not as familiar with the those specific components, but if it's something that you would typically do ultrasonic thickness inspections on, it could potentially be an option.
That's very interesting.
Yeah, I was just going to say I would agree with that too, but I know I'm sure Barry's waiting to chime in and say that you could just, control that with cycle chemistry and prevent it, but having that monitoring check as well is extremely valuable.
Yeah, Kane, there was many questions. I didn't highlight them. Probably more questions about some of those very important aspects of HRSG damage and failure than there was about the monitoring. So, I think because they knew I was going to be involved, they asked about exfoliation, steam side exfoliation, cycle chemistry, FAC, which you just mentioned, external tube cleaning, and real-time corrosion monitoring. And I think I thought that the emphasis was, will this monitoring system be able to address any of those, And I think it was quite interesting set of questions.
Yeah, no, there's definitely a lot more that can be done with monitoring. I would say in our initial focus, we've kind of, dealt with creep and fatigue issues primarily, and corrosion fatigue on drums, etc. But as you said, the sky's the limit on what you can do with this monitoring. So.
Yeah. I noticed in Eugene's introduction, one of the goals was for oxidation and exfoliation. I think that would be very difficult to do from specifically those incidences. Bob and I have done a lot of work with the exfoliation in HRSGs causing failure, because you can use the oxide thickness to internal oxide thickness to estimate the temperature, and so there's a lot of work being done on that. Maybe that's one of the things that we can look at in the future.
Yeah, I mean, I would definitely agree.
The interesting one, Bob, because we always have a lot of discussion in these meetings, was on external tube cleaning, of whether these systems could be used to predict when the tubes actually needed cleaning.
Well, that's an interesting point. I mean, I guess the key there is going to be having accurate gas side pressure readings in all the right places to monitor the draft loss across each section. So I don't see any reason you couldn't do that and do some analysis, informed analysis like you're doing on these other things to try to get a little more intelligent decision of when it's cost effective to clean. It's probably easier than some of the rocket science stuff you're doing now. I always found this real-time hanger movement measurement interesting, and it seemed to me people aren't maybe using that as much as they could find benefit from. I know it's very, very difficult to make thorough hanger inspections at the right times, hot and cold, and do it repeatedly and collect the data, and even have physical access to take hanger readings manually. So are you seeing more interest than at the plant the case study covered in the hanger and pipe movement monitoring?
Yes, I would say, to me, the big push that we've seen for people is on the areas of the systems, piping systems, where you can't walk down or you can't get a good perspective to, as you said, timing to just monitor those pipe movements. But I would say we haven't seen as much a push for that, just because a pipe hanger is usually out in the middle of space and people don't think about it till it falls off. To me,
yeah, well, that's sort of why having the data and preventing it falling off can be useful.
Bob, so this is Matt Freeman, and I'll chime in on that. I've been surprised. It's something that people haven't asked for. We haven't necessarily promoted it either. But I think, like you, and just because I think because Kane kind of leads this effort for structural integrity, and he's more excited in calculating creep and fatigue when he has all the data that he can do. But certainly we see value in monitoring the hanger movement. And as you saw, from Jacob's presentation, in that case we use string potentiometers. We've also done some things with LiDAR as well, and the limitations on LiDAR that we tested had more to do with if you were outdoors and lighting affecting the position. But it's something that in the last 2 months we've had a lot more discussion about, certainly with NSI, and saying, hey, maybe it's something that we should
maybe
people more about.
Maybe we'll have more case studies later.
Yeah.
Okay.
Mm-hmm.
I see no more questions. We have 3 minutes. Anybody got a parting shot?
Exactly on time, I think. Well done, Matt and Kane and Wes and Eugene.
Yeah, excellent job, guys. Very good. Very nice session. Scott, you have any final words for us? I think Scott has gone to lunch. maybe.
Gone to Brazil, I think.
So there's a survey is going to pop up for all our attendees that we would like for you to fill out so that we can continue to, present the most interesting topics on HRSGs and cyclochemistry to you. And also, if anybody's interested in presenting at one of the upcoming HRSG forums, you can put your information in there as well, and we'll reach back out to you.
Yeah, Scott, you forgot to mention the HRSG meeting in Australia next week. People are absolutely welcome to hustle on down and join us in Brisbane.
Yeah, hop on the plane and get down under. A couple of questions came in about will the presentations be available? We'll be sending out a copy of the presentation recording in a couple days, and hope you enjoy it and share it with your colleagues.
Okay, very good. Well, thanks everyone, and thanks all of you that attended. And we'll see you in June, if not before that.
Good, thank you.
Thanks, everyone.
you.
Yes.
Bye-bye.